using caching.
Hello, I'm Sebastian Burkhardt. I work at Microsoft Research, and this is work I did together with an intern about 2 years ago, Tim Corpeters from Belgium. So the problem that we looked at has to do with the environment in which we were studying applications, and I will talk quite a bit about that. So there are actually 2 talks in here, and I don't have time to give both of them all the justice they deserve, so I'll have to hurry a bit probably. But to me, the interesting starting point is the world of composed, scalable, distributed services, because this is the world we're moving into. A lot of programs are written that way. In that world, one thing we can look at is this problem of keeping a view of distributed state fresh. So a very specific problem. And the solution we came up with is sort of a classic algorithm type solution, where we have an algorithm that can track dependency and propagate changes automatically. And we have an evaluation that shows that it is better than polling, and it is close to a handwritten, manual change propagation algorithm. Now, when we submitted this, it didn't get immediately accepted, so we had to do more work. And a lot of the extra work had to do with making clearer what this is all about. So we spent extra time formalizing the entire setup so that we can explain what does this even mean, what are composed, scalable, distributed services. And as a result of that, we ended up with a fairly small, nice calculus that explains that. And people can use that as a reference to what is this all about. So even if you don't care about this problem here, you might still care about the calculus and vice versa. So it's very possible that you only care about one of those things. So what are these composed, scalable, distributed services? So I would call this the contemporary look of distributed programming. And what that means is when people build these services in the cloud, they take components, they put them together, and these components include both stateful and stateless services. So they're put together usually using RPC calls, which are like REST services most of the time. And there are a couple interesting things here to look at. So first of all, there is a notion of failure that is important. So all of these things can fail. And you do different things about it. So if a stateless service fails, it's easy. You just restart it. If a stateful service fails, it's a little harder. You have to recover from the durable state that you have stored somewhere, like in cloud storage or in replicated copies. Finally, the requests themselves can also fail. So you may send a request, never get a response, you don't know what happened. People deal with this usually by making these requests retriable, so you can try it again. They're idempotent. That's sort of the standard way to approach this. Another important thing, though, so this is one thing that makes this not just composition of software modules, right? Another thing is these things have to scale. So if you don't have to scale this, forget this entire talk. Really, this is about making this scalable. What that means is these services internally have to have the ability of scale beyond the load that fits on a single machine. Things are a lot easier with single machines, but in order to do that, they have to have partitions that can be distributed over clusters whose size may vary at runtime. You may need more machines than you anticipated or fewer. So let me give you an example of how you could write an application like this. So this is called Chirper. It's our running example. It's any kind of social application. So clients can add posts to their own timeline. So I would have like a call user.post. I can also unpost if I might delete my post. I have another microservice on the right that is called timeline. So I sent this to one service called post. And just assume these are like 2 microservices written by different teams in my organization. So I could also send a user.follow to my timeline, which the timeline records who I am following. And then finally have a called user.getTimeline, which is supposed to sort of aggregate my timeline from my own posts plus all the posts of people that I'm following. So what would it do? Well, it would have to go, and when I call this on timeline, timeline in turn has to get to various posts to get all the posts of different users. So the important thing here is both of these services are partitioned by user. So they're logically independent per user. So there's a fine-grained internal partitioning. And I have shown this sort of by you making user be not the first argument, but sort of something before a dot. So if I call user get timeline, some code will run in there. I target this at one of the partitions. Then that partition will determine where to get the data from, and it will contact one or more other partitions in that service to get the data and put it together. So the important thing to see here is that the data that is required to compute the result of this request is distributed among multiple services and partitions. So it's not just in one place. And the code that you would use to write this composition in the timeline service could look something like this. This is pseudocode, but you get the idea. So I might be sending a request to get my own posts from the service, and then I send a bunch of parallel requests to get all the posts by the users I'm following, and finally I'm putting them together in one container and sending them back to the user, something like that. So our first contribution was to take this model and turn this into a calculus that is small, but has all the features needed for this example. And we also proved preservation and local progress, which was somewhat interesting. There are non-trivial challenges here, like you cannot serialize function types. So there's a little collection of challenges in there. So I won't go into the details just so that you believe that it is not a very large calculus. This is the syntax of the calculus, but I will not talk about it. I don't have time, really. Okay, so another thing I want to point out here is how did I arrive at this calculus? Well, I didn't actually invent this as much as distill it. And my starting point was the Orleans framework. So this notion of composed partition services really is the same as the virtual actor model, which was published by the Orleans team for their framework. They use different terminology. So what I would call service, they call it grain class, and then the service partitions are grain instances. And the partition keys are grain keys. And those grains are packed into silos, which I don't really have a term for that, but I just call it host machine. But I want to point out that I actually took this structure from their framework, turned it into a formal thing. Okay, so that was kind of the first part. Oh, I should also mention Orleans, by the way, is very popular inside and outside of Microsoft. So you can use it to build these types of scalable services. We have, for example, all of Halo's web services are built using this. And there's an open source community that is maintaining this. So if you're having to build one of those services, it's worth having a look at this. Anyway, that was the first talk. Now I'm going to go to the second talk. So in this setting of composed services, the problem I want to solve is keeping views up to date. So I go back to my same example I had before, and I'm saying, how do I keep that timeline up to date? So I called this once on my client. I got a timeline, but I'm now staring at my screen, and I want any changes that are made to appear on my screen fast. And fast is the important thing. Fast meaning much faster than a second, say. Which is not the case typically for something like Twitter. You don't really care, but it's just an example. So imagine something where you actually do care about speed. So one thing I can do is polling. It's very simple. So what do? I just repeat. So I have something like a loop here where I get my result by one time, and then I wait, say, 5 seconds, 20 seconds, 30 seconds. You make it up, whatever you want. And then I try again, and I will get consecutive results. So clearly this works. Clearly it's very easy to understand and write. You have good failure behavior. Like if one request fails, no big deal. Maybe the next one will succeed. No problems. But it's also really not suitable for fast refresh. So why is that? So if you're trying to make this delay really small, what happens is your server load explodes. You cannot have a lot of clients sending you multiple requests per second. It will just cost way too much. So we really need something faster, something better for fast. Now, what do we have? So there's actually a lot of work on this. So there's a lot of work on how to write programs that do low latency change propagation. And all of these are well studied and they work. For example, we have some of them work much better than others. So one thing that is hard to use, for example, is the observer pattern. Don't really recommend it. It works if you have to use it, but it's hard to keep your code clean and maintain the state correctly. PubSub services work, but even there, it's actually pretty hard to get the subscription correct under data races and failures. Not so trivial to do that right. And then finally, probably the best solution is to use reactive programming, in which case you have a framework that lets you express queries directly at a high abstraction level for your query. This works great if your query is actually a query that you can easily express. It might not be so easy if your query if the thing that you're querying turns into a very complicated query with joins. So joins are typically the sticking point for this, both from a perspective of programming complexity as well as implementation performance, because joins are often hard for runtimes to execute efficiently without detailed knowledge of the structure of the data. So the thing I want to sort of question here is, do we really have to re-architect the service? So all of these solutions assume that you're going to happily change your code to get these features. And what I want to push here is the idea that you don't have to change your code. So if I have written my code using this composition of services, there is actually enough information there already to know what depends on what and exploit that. So what I'm proposing to do here is to keep the same service architecture and then have a new API on the client that looks like polling, but internally actually uses pushing for efficiency purposes. So what does that mean? For example, it could look something like this. So instead of I still have my loop that says while interested, but now before the loop, I create the object that represents this continuous, continuous query. I put the code in there that I want to execute. And then, by the way, I have to also dispose that at the end because that incurs some continuous cost while it is active. But then in the loop, I have a loop again where I repeatedly fetch the result, just as for the polling. But the semantics is different now. When I first call this, it's the same. I just get the first result, which is my timeline, my entire timeline the first time around. But the difference is, when I call again, it will block until it's different. So instead, this loop does not just keep going. It actually blocks until the result has changed. Only then do I go around again. So this is what makes it efficient, because essentially this thing is just hibernating until changes happen. And the error handling is the same. Now, how do we implement this? So we started with the virtual actor framework, which is the Orleans project. So we have a framework to pin this on. We need to put this into a framework. Otherwise, we don't know what are calls, what are responses. We don't have the framework. But you could put this into other frameworks. And then we add the algorithm piece, which is what we call reactive caching. This is really the part where we maintain caches of calls, and we maintain their dependencies, so we know when they change. So let me illustrate this a bit. So what we're doing is we maintain something called a summary. And this should remind you of something like memorization. So a summary is a combination of a particular method call together with all of its arguments. And it saves the result and its dependencies. And then in addition to summaries, we keep caches. So there's two pieces to this story. There's the summaries and the caches. And how are they connected? So here's an example of, supposedly, these are my partitions on different machines. Every write box is on a different machine. And I have my client. So when it executes this user timeline thing, the client, it calls get timeline on the user timeline, which in turn calls all these partitions below. And what I'm doing now is I'm saving these black boxes. These are the summaries. These are the things, the call plus the result, and it will be stored. And then another thing I'm storing is the caches, which is those are at the same place where they're being used. I'm storing the summaries that were consumed. And the caches stay connected to the summary. So a cache is just a copy of a summary on a different node. And I maintain a bidirectional connection between the cache and the summary that it is caching. So the important thing here is, and you can sort of read this out, you can read the entire algorithm just out of the following statement in some senses. This is a stable state because all the caches match the summaries they represent, and all the summaries match the computation when computed on the local caches. So now what we have to do, if anything about that invariant changes, we can locally repair it. And that's really the algorithm in a nutshell. So let me illustrate this. So this is, suppose, for example, that I have on the rightmost side here, I am adding a message which will change the overall result of the computation. It's actually here. Let me see. Let me just go there. Okay. So I'm actually adding a message. Chris posts a message to the grain there. So what happens is the summary gets invalidated. This is what I mean by that crossed out. So I mark the fact that this summary needs to be recomputed. So when the scheduler gets around to it, it will recompute this summary. And in this case, it will determine that the result has changed. If the result hasn't changed, by the way, we're done. We don't have to send any messages. If it has changed, we send the message with the new summary to the remote cache. So now this cache gets updated. But because this cache was used by this summary also gets now invalidated. So again, when the scheduler gets around to it, it will execute this summary again. And now it will compute one more message in the timeline. The important part is it didn't re-execute the queries to the remote participants because the other things were still cached, and those caches were still valid. So the whole savings comes really from the fact that you hid in the cache. And then now the new summary is again propagated further on to the client, and the client can deliver it to the reactive polling loop. So you can see how this recursively repairs. And the thing I want to kind of point out here is that it's like a way of storing a computation and repairing it incrementally. So I did not look, there was no central authority that repaired this graph. It was just locally detecting that something is wrong and then taking appropriate measure. So this is efficient because it only took 2 messages, to get the new value to the client. It's also asynchronous. Nothing was locked here. It's interleaving with the other scheduler. And it was parallel. So if you have multiple changes happening in this computation, they would all be propagating in parallel. So I think of this as a different way of incrementality. So when we see reactive programming, we often get the type of incrementality where state is incrementalized. Here what we're doing is we're incrementally repairing the computation. So how about consistency? So consistency is not perfect here, but neither is it perfect when you do polling. So let's just compare this a bit. So when I do polling, I don't have global consistent snapshots in neither case. Do I see all the intermediate values? No. Why would I need to see all intermediate values? I only care about the latest. However, do I get causal consistency? Unfortunately, no. So this is room for improvement. There is probably a way to make this algorithm better. Right now, this is where we are weaker. However, the good news is if you see anything that isn't consistent, it's always temporary. So this is what we prove. If something about what you're seeing is stale or inconsistent, then you're guaranteed to receive a new result. It's already in the works. Okay. So there's an automatic fault tolerance, but time is pretty short. I want to just say that the trick is to consider failure domains. The only concepts spanning failure domains here are those connections between the cache and the grain. So the only thing we have to repair is if one side of that relation fails without the other failing, it's actually easy in both cases, but I will, unfortunately, because of time running out, I will not explain this right now. But this is an important part, like how the failure is repaired. So benchmarks, again, I probably need to be brief here. So we did both. We have 2 relatively small and simple benchmarks. The baseline latency, basically what we're showing here is our thing is out of the picture. It's just Orleans. We're comparing the cost of a parallel query with a sequential query executing. On the right, you see the message diagram. And then the reason why we execute this without our stuff is now if we add our reactive caching, you can see that it gets a little slower. So these are median and quartiles. And you can see I'm a little slower. So this is the extra time I took to construct all these dependencies and maintain them. But it's not It's not super slow, and there's probably room for improvement. We haven't optimized so much yet. But the important part is if we hit in the cache, we're super fast. So anything that's cached is great. Now, for the throughput, we have measured throughput by checking how much the throughput goes down if we add our stuff. So in this diagram, you can see from left to right, we increase the load on the service. And these lines, each line is one experiment. The top group of lines is running without change propagation at all. So we have just somebody reading and updating, but changes are not propagated. So in that case, the peak throughput we can get is close to 120,000 requests per second. But then once we turn on change propagation, that this goes down. And you can see it goes down more or less for different schemes. Since I don't have much time, I'll just jump to sort of the high-level message. So low-frequency polling is actually good. So this is one of the, I don't want to just push my solution. So if you're actually happy with bad latency, then doing a low-frequency polling has very good throughput characteristics. It's very modest in its resource consumption. However, high-frequency polling is pretty bad because, again, you're overloading the service. Generally, our performance is competitive with handwritten propagation. We are a bit slower, mainly because of scheduling non-optimal behavior, which could probably be improved. One place where we are better than handwritten propagation is you have super heavy load, in which case our back pressure optimization will make this better than handwritten propagation. So you would have to also implement the back pressure for that. Okay, and for user-perceived timeliness, so we measured missed deadlines in a simulated user environment. And in this case, really polling is not competitive at all because it misses a lot of deadlines. So this is my last slide. Again, I'm just showing conclusions, contributions. I'm open for questions. Thank you.
Questions? Okay, so this is a very nice talk. So I was wondering, how do you, if you have functions that depend on a lot of hosts,
yes.
How do you pick which information to save to avoid blowing out the local size, the local memory of a host?
Right now, so right now, it's basically just we save, whenever you do one of these reactive computations, we save all the things you depend on, but it's reference counted. So when your observing thing goes away and nobody observes this cache entry anymore, it disappears. So there's probably more we could do at some point. Yeah, thanks. Yes?
Thanks for the talk. The programming interface still looks a lot like callbacks. Why not using full reactive programming, say streams?
So I need this.
The programming interface for the user still looks like a callback, right? So you get the value, and then you process the value. Why not?
It's not exactly a callback because you're asking for the value, and you get it as a return value of the thing you're asking for.
Isn't that equivalent to registering a callback and executing it when you get the value?
Well, it's more convenient because you don't have, if you have looked at code that does multiple callbacks, it gets very ugly. So this is the async await style of thing.
All right, thank you.
It ideally combines with something like React, where you want to update your entire model when you get new results.
Any more questions? Oh, there is one more question. Okay, last question.
Hi, you addressed this a little bit, but I was curious. If I wanted something stronger than causal consistency, what are my options?
Stronger than causal consistency?
Stronger than causal consistency, yeah.
So in this context, I don't think I can give you options for that. It's expensive. I guess if you really wanted that, the best thing would be you have multi-version state, creating some kind of snapshot. But now your ambition goes way beyond what this does, and the cost for that may also be much higher. But in a system with say distributed transactions, you could definitely do that. I have also worked on such a system.
Okay, let's thank the speaker.